High above the Atlantic Ocean, on one of the Canary Islands, a team of pioneering scientists is setting up an experiment that will span the vast scales of the cosmos and could confirm our perception of the universe is an illusion.
I'm checking the signals from the cosmic random number generator, and it looks pretty good.
They're connecting two of Europe's largest telescopes and attempting to use galaxies billions of light years away to control intricate measurements of tiny particles of light here on Earth. They're testing the existence of perhaps the strangest idea in science: quantum entanglement.
Entanglement is this very powerful but strange connection that exists between pairs of particles.
The effect is almost magical, as if something here can mysteriously affect something there. Can particles be connected as if they're joined together, even if they're millions of miles apart?
Entanglement opens up new venues for communication, for computation, and for understanding the nature of space and time and the beginning of the universe.
Einstein rejected the idea, calling it spooky action at a distance.
It's so beautiful, but what the heck is behind it?
So, is entanglement real? Do we live in Einstein's universe of common sense laws, or a bizarre quantum reality that allows strange connections across space and time? Will the team prove Einstein right?
Moving.
Or wrong?
Yeah, that's good. We do have a test. We are acquiring data right now.
As with so many of the most important ideas in physics, the story of quantum entanglement begins with Albert Einstein. In 1927, he traveled to Brussels to attend a meeting about a new theory that described the microworld of atoms and tiny particles: quantum mechanics.
Quantum mechanics is one of those amazing intellectual achievements in human history.
For the first time, scientists were able to probe a world that was until then quite invisible to us, looking at the world at the scale of atoms, 1,000,000 times smaller than the width of a human hair.
One way to think about the scales is that if you take an everyday object, like a soccer ball, and you enlarge that soccer ball so that actually you can see the individual atoms, you roughly have to make it the size of the Earth, and then move into that planet. Then you are in the world of atoms and particles.
It was the nature of fundamental particles that make up the world we see around us that Einstein had come to Brussels to discuss. And it was here that Einstein entered into a heated debate that would lead to the discovery of quantum entanglement, a concept that will trouble him for the rest of his life. With 2 PhDs from Harvard and now a leading professor at MIT, David Kaiser has studied this dispute and has come to the place where it all began.
This is the original Solvay Institute building, beautiful grand building. And this is the place back in October 1927 where the 5th Solvay conference was held. This amazing week-long series of discussions on really what the world is made of, on the nature of matter and the new quantum theory. And these steps are the very steps on which this famous group photograph was taken. It's a collection of some of the most brilliant people in the world. Here in the front row, we see Albert Einstein and the great Marie Curie and Max Planck. In the back row standing, the dapper Erwin Schrödinger, and these sort of brash 20-year-olds or mid-20s, Werner Heisenberg and Wolfgang Pauli. I had a huge version of this photograph up on the walls, a poster in my college dorm room. My roommates had their favorite bands, and I had the 1927 Solvay conference, which says a lot.
This was one of the greatest meetings of minds in history. More than half were or would become Nobel Prize winners. Their experiments were showing that deep inside matter, tiny particles like atoms and their orbiting electrons were not solid little spheres. They seemed fuzzy and undefined.
So this group here, these were the folks who had just been plumbing deeper and deeper and deeper to find what they hoped would be a bedrock of what the world is made of. And to their surprise, they found things less and less solid as they dug in. This world was not tiny little bricks that got smaller and smaller. At some point, the bricks gave way to this mush. And what looked like solidity, solidness, in fact, became very confusing and kind of a whole new way of thinking about nature.
The theory of quantum mechanics presented that the meeting was strange. It said that a particle like an electron isn't physically real until it is observed and measured by an instrument that can detect it. Before it's detected, instead of being a solid particle, an electron is just a fuzzy wave, a wave of probability.
These objects like electrons and atoms, when we describe mathematically their behavior, the only thing we can describe is the probability of being at one place or another.
It's like a wave of all those different possibilities. It's not that the electron is in one place or the other, we just don't know. It's that the electron really is a combination of every possible place it could be until we look at it.
Laws of nature were no longer definite statements about what's going to happen next. They were just statements about probabilities. And Einstein felt, well, that's defeat. You're giving up on the heart of what physics has been, namely to give a complete description of reality.
For Einstein, the idea that tiny particles only pop into physical existence when they're observed is akin to magic. He later asked a friend, "Do you really believe the moon is not there when you are not looking at it?" Outside of the formal setting of the conference,
Bonsoir.
he challenged the most vocal supporter of these ideas, the great Danish physicist Niels Bohr.
Einstein would show up to breakfast at the hotel, and Niels Bohr would be there, and Einstein would present his latest challenge. Niels Bohr would sort of mumble and wonder and confer with his younger colleagues. They'd head off to the formal meeting at the Institute, and somehow every night by supper time, Bohr would have an answer. One of the observers said that Einstein was like a jack-in-the-box. Every day he'd pop up with a new challenge, and Bohr would flip this way and that, and then by supper have crushed that one, and it would start all over again.
To Bohr and his colleagues, quantum mechanics not only explained experimental results, its mathematics were elegant and beautiful. And since Einstein hadn't found flaws in their equations, they left the Solvay meeting feeling more confident than ever in their ideas. But Einstein didn't give up. In 1933, Einstein, a Jewish scientist and outspoken pacifist, fled Nazi Germany and took a position at the Institute for Advanced Study near Princeton. He recruited two physicists to help him, Nathan Rosen and Boris Podolsky. And in 1935, at afternoon tea, the three men formulated an idea that would shake the very foundations of quantum theory. They discovered quantum entanglement. Today, Robert Dijkgraaf is the director of the Institute.
I think scientific progress is often made in kind of a dialogue. And I think the informal moments are crucial So at the Institute for Advanced Study, we've had tea at 3 o'clock from the very beginning.
It was here that a conversation between Einstein and Rosen sparked a powerful idea.
Rosen told him he was studying a system of 2 hydrogen atoms and noticed that there were some ways in which these 2 atoms were coupled, even if you move them very far apart. And then apparently Podolsky jumped in and said, well, Professor Einstein, this is very important in your arguments showing that quantum theory is incomplete. So they got this very animated discussion, and what kind of happened still is now you have a bunch of scientists discussing, and at some point someone says, let's write a paper together. So they did.
Their paper, known today as EPR, argued that the equations of quantum mechanics predicted an impossible connection between particles, a seemingly magical effect. It would be like having 2 particles, each hidden from view. Looking at one mysteriously causes the other to reveal itself too, with matching properties. Quantum theory suggested this effect could happen in the real world, for example with particles of light, photons. The equations implied that a source of photons could create pairs in such a way that when we measure one, causing it to snap out of its fuzzy state, the other mysteriously snaps out of its own fuzzy state at the same instant, with correlated properties. The 1935 paper that described this effect has become Einstein's most referenced work of all. It has captivated generations of scientists, including one of the world's leading quantum physicists, Professor Anton Zeilinger.
The Einstein-Podolsky-Rosen paper fascinated me, and I had to read it at least 5 or 6 times until I finally understood what goes on. And then it didn't let me go again.
Another way to think of the paired particles is to imagine a game of chance that's somehow rigged.
Suppose I had a pair of quantum dice. I put these 2 quantum dice in my little cup, throw them. I look at them, they show the same number, 6. I put them again in the cup, throw them again. Now they both show 3. I put them in again, throw again. Now they both show 1. Point now being, what I see here is, I see 2 random processes, namely each die showing some number, but these 2 random processes do the same. That's really mind-boggling.
How could 2 particles act in unison, even when they're separated from each other?
Essential to the EPR argument is that these particles can be separated at an arbitrary distance. One could be here at Princeton, one could be in the Andromeda galaxy. And yet, according to quantum mechanics, a choice to measure something here is somehow instantaneously affecting what could be said about this other particle. You can't go from Princeton to Andromeda instantly. And yet that, they argued, is what the equations of quantum mechanics seem to imply. And that, they said, so much the worse for quantum mechanics. The world simply can't operate that way.
For Einstein, this strange effect conflicted with the most basic concept we use to describe reality: space. For him, objects, particles, everything that exists is located in space. Space, together with time, was the key ingredient in his theory of special relativity with his famous equation, E = mc squared.
Einstein, of course, was the master of space-time. He thought that if something happened here, that shouldn't immediately and instantaneously change something that is going on over there, the principle of locality, as we currently call it.
For Einstein, it's simply common sense that if objects are separated in space, for one to affect the other, something must travel between them. And that traveling takes time. Quantum particles acting in unison could be explained if they were communicating. One particle instantly sending a signal to the other, telling it what properties it should have. But that would require a signal traveling faster than the speed of light, something Einstein's theory of special relativity had proven impossible. And it would mean the particles were fuzzy and undefined until the moment they were observed. Instead, Einstein thought the particles should be real all along. They must carry with them a hidden layer of deeper physics that determines their properties from the start. Almost the way that magic tricks, while appearing mysterious, have a hidden explanation. But this hidden physics was missing from quantum mechanics. So, Einstein, Podolsky, and Rosen argued that the theory was incomplete.
Podolsky was very enthusiastic about this project. In fact, he was so enthusiastic that he ran to the New York Times and told them the news. So Einstein read in the newspaper that he has proven quantum theory is incomplete and possibly wrong, and he was very much upset by that. So he writes a letter to the editor saying this is not the way one should communicate in physics, and he was really upset with Podolsky, and apparently he didn't speak to him anymore.
When Niels Bohr heard of Einstein's paper, he wrote an obscure response, arguing that one particle could instantly influence another. This seemingly impossible phenomenon became known as quantum entanglement. But Einstein dismissed it as spooky action at a distance. No one can think of an experiment to test whether Einstein or Bohr was correct. But that didn't stop physicists and engineers from making use of quantum mechanics in the lab.
In the 30s and 40s, the debate around the EPR paper sort of dies down, but quantum theory actually takes off. The mathematics leads to all kinds of amazing developments.
The equations of quantum mechanics accurately predict the behavior of atoms and tiny particles, enabling the scientists of the Manhattan Project to develop the bomb. And in the years after the Second World War, researchers at Bell Labs in New Jersey used quantum theory to develop the first lasers.
In our laboratories, men experiment with a light once undreamed of in the natural world.
And build small devices that could control the flow of electricity, transistors.
It's destined to play a vital role in your future, your electronic future.
Transistors became the building blocks of the burgeoning field of electronics. Computers, disk drives, the entire digital revolution soon followed, all made possible by the equations of quantum theory. Yet Einstein's questions about entanglement and what it implied about the incompleteness of quantum mechanics remained unanswered until the 1960s, when a physicist from Northern Ireland made a remarkable breakthrough, John Bell.
Bell was a very talented young physics student, but he quickly grew dissatisfied with what he considered almost a kind of dishonesty among his teachers.
Bell insisted that Einstein's questions about quantum mechanics had not been addressed.
He got into shouting matches with his professors. Don't tell us that Bohr solved all the problems. This really deserves further thought.
Quantum mechanics has been fantastically successful, so it is a very intriguing situation that at the foundation of all that impressive success there are these great doubts.
It's a very strange thing that ever since the 1930s, the idea of sitting and thinking hard about the foundations of quantum mechanics has been disreputable among professional physicists. When people tried to do that, they were kicked out of physics departments. And so for someone like Bell, he needed to have a day job doing ordinary particle physics. But at night, hidden away, he could do work on the foundations of quantum mechanics.
Bell became a leading particle physicist at CERN in Geneva, but he continued to explore the debate between Einstein and Bohr. And in 1964, he published an astonishing paper. Bell proved that Bohr's and Einstein's ideas made different predictions. If you could randomly perform one of two possible measurements on each particle and check how often the results lined up, the answer would reveal whether we lived in Einstein's world, a world that followed common sense laws, or Bohr's, a world that was deeply strange and allowed spooky quantum connections.
We now know with hindsight this was one of the most significant articles in the history of physics, not just the history of 20th century physics, in the history of the field as a whole. But Bell's article appears in this, sort of out-of-the-way journal. In fact, the journal itself folds a few years later. This is not central to the physics community. It's sort of dutifully filed on library shelves and then forgotten. It literally collects dust on the shelf.
A few years later, completely by chance, a brilliant experimental physicist stumbled upon Bell's article.
I thought this is one of the most amazing papers I had ever read in my whole life. And I kept wondering, well, gee, this is wonderful, but where's the experimental evidence?
At the University of California, Berkeley, John Clauser was desperate to put Bell's idea to the test in an experiment. He had a talent for tinkering in the lab and building the parts he needed.
I used to rummage around here and scavenge and dumpster dive for old equipment.
He knew where to find hidden storage rooms like this, which he could raid to salvage spare parts for his experiments.
And this was a power supply for diode lasers. That looks like something I built. Stratton. This is one of this is my book. I think this may be my old book. I'll take it.
Deep in the basement is John's old laboratory.
This is B207, where we did the original experiment.
He hasn't been back for decades.
I remember distinctly this old sink. These computers were not yet invented. It was hard work. We spent long hours, weekends, evenings, you name it. We believed, although nobody else did, that it was actually a very significant and important experiment.
Back at home, John has kept parts and papers from his experiments.
Careful, don't.
Where's this?
So this is my shop and laboratory. Mostly now I just build sailboat parts for yacht racing. Here's a picture of the experiment I did. I had more hair in those days. Here's another picture. This is Stu Friedman, worked on it with me. Two entangled photons would go out in opposite directions through lenses into the polarizers. That could be, in the simplest case, the lenses in a Polaroid sunglasses.
John Clauser and Stuart Friedman constructed the world's first Bell test experiment. They focused a laser onto calcium atoms, creating pairs of photons that the equations of quantum theory suggested should be entangled. They recorded whether or not the photons passed through polarization filters on each side, and checked how often the answers agreed. After thousands of pairs, if the results were more correlated than Einstein's physics predicted, the photons must be spookily entangled.
We saw the stronger correlation characteristic of quantum mechanics. We measured it, and that's what we got.
The outcome was exactly what Bohr's quantum mechanics predicted. The experiment appeared to show that the spooky connections of quantum entanglement did exist in the natural world. Could it be that the great Albert Einstein was wrong? The first people to react to this extraordinary result were not the world's leading physicists.
Ronald Reagan's definition of a hippie was someone who dresses like Tarzan, has hair like Jane, and smells like cheetah.
A small group of free-thinking physicists at the heart of San Francisco's New Age scene got in touch with John.
They call themselves the Fundamental Physics Group. They spelled physics with an F. Some members would experiment with psychedelic drugs. I mean, they were kind of in the flow of the kind of hippie scene. And that group was just mesmerized by the question of entanglement.
The idea was just to discuss fringe subjects with an open mind, and I thought, sure, that's kind of what I do. They were doing their best to link Eastern mysticism with quantum entanglement. They sold a lot of popular textbooks. There were a lot of followers.
Their books became bestsellers, like The Tao of Physics, which highlighted that Eastern philosophy and quantum entanglement both described a deep connectedness of things in the universe.
It was the great cosmic oneness.
The group held meetings at the iconic Esalen Institute.
It was a marvelous, beautiful place where they would discuss all of these ideas. It was right on the Pacific coast with the overflow from the hot tubs cascading down the cliffs into the Pacific Ocean. To my knowledge, no useful connections to Eastern mysticism were ever discovered by the group. But it was fun.
The Fundamental Physics Group may not have uncovered the secrets of cosmic oneness, but in seeing entanglement as central to physics, they were decades ahead of their time. In the years after Clauser and Friedman's pioneering work, physicists began to test possible loopholes in their experiment. Ways in which the illusion of entanglement may be created, so the effect might not be so spooky after all. One loophole is especially hard to rule out. In modern Bell test experiments, devices at each side test whether the photons can pass through one of two filters that are randomly chosen, effectively asking one of two questions and checking how often the answers agree. After thousands of photons, if the results line up more than Einstein's physics predicts, the particles must be spookily entangled. But what if something had mysteriously influenced the equipment, so that the choices of the filters were not truly random?
Is there any common cause deep in the past, before you even turn on your device, that could have nudged the questions to be asked and the types of particles to be emitted? Maybe some strange particle, maybe some force that had not been taken into account, so that what looks like entanglement might indeed be an accident, an illusion. Maybe the world still acts like Einstein thought.
It's this loophole that the team of Austrian and American physicists is working to tackle at the High Altitude Observatory on the island of La Palma in the Canaries. With quantum mechanics now more established than ever, they're determined to put entanglement to the ultimate test and finally settle the Einstein Bohr debate beyond all reasonable doubt. Professor Anton Zeilinger is leading the team.
So we are now going up the mountain towards the Roque de los Muchachos. So everything looks perfect today.
They're creating a giant version of Clauser and Friedman's Bell test, with the entire universe as their lab bench. In this cosmic Bell test, the source of the entangled particles is almost exactly 500 meters from each of the two telescopes. The team must send perfectly timed pairs of photons through the air to each side. At the same time, the telescopes will collect light from two extremely far-off, extremely bright galaxies called quasars. Random variations in the color of the quasar light will determine which filters the photons must pass through. And since the light from the quasars has been traveling for billions of years to reach Earth, it makes it incredibly unlikely that anything could be influencing the random nature of the test.
At this experiment we use 3 locations. One is behind me here, where you see this container with the blue frame. In that container we have the source for the entangled pairs of photons. One of the 2 photons is sent to one telescope, the other one to the other. The first telescope is here, the Telescopio Nazionale Galileo. It's an Italian telescope. You can see the small container on the bridge there, where the photon arrives, and the telescope then will look up on the sky, pick up the light from a quasar, which is very, very far away, and take the signal of the quasar to steer the kind of measurement done on the photon which arrived. Over there is Herschel, William Herschel telescope, the big one. The photon arrives there, and again that telescope picks up the light from a different quasar, and that steers the measurement on the photon here. The preparation right now is that at the source, I would claim that we have some of the best people in the world working on these quantum sources.
By firing a laser through a specially made crystal, the team creates a pair of photons that quantum theory suggests should be entangled.
We have some entanglement, just about the best we've seen here. We still have to tune the state a bit to get to what we usually achieve in the lab.
Then the next step, also being done at daylight now, is to try to couple the 2 positions to each other with lasers to make sure that they really see each other and everything works.
Fahren wir nach oben und unten, Johnny, okay?
Okay.
1, 2, 3, 4, 5. Okay.
And also in parallel, they are making big lists of possible quasars.
This is our favorite pair of quasars. One of the quasars emitted its light something like 12 billion years ago. And the William Herschel telescope is going to look at a quasar that's coming up from the horizon throughout our 2-hour observation period, getting higher and higher in the sky. Galileo telescope is going to look at this other quasar that's sweeping out on the sky.
In the end, it could be running smoothly, or there need to be a couple of decisions made, in an excited state in the last instance.
With the experiment finally set up, the team take their positions. Professor David Kaiser has worked on this experiment with his colleague Jason Galecchio for 4 years. Coordinating it all is Dominic Rausch. The experiment is his thesis project. He's also been preparing for years. But as darkness falls, temperatures on the mountain begin to drop.
Ja, ja, Sie haben unsere Nummer und wenn es besser wird, werden wir angerufen.
Okay. Okay, großartig.
Ciao.
Okay, there's bad news. They have been told to leave the Wilhelm Herschel because the road will be so dangerous, too dangerous, so they have to go down now. Yeah.
The team has been instructed to leave the telescopes. The extreme weather could quickly make their route off the mountain too dangerous. After all the preparation, it's devastating news.
Hello guys, we should go down.
Yes.
There seems to be a serious ice problem in the road.
Okay. We'll be called back if things work out, I guess.
Happens.
Yeah.
What can you do?
The next day, the team begins to prepare for another attempt. As the sun begins to set and the experiment start time approaches, Johannes Hansteiner checks the equipment hasn't been affected by the weather.
What are you doing, Johnny?
I'm currently checking the signals from the cosmic random number generator, checking if we have a high enough signal, and it looks pretty good.
But now, the air is thick with clouds.
Here's the humidity at the various telescopes, and you see the humidity is 100%. So as long as this lasts, we can't do much.
The teams at both telescopes wait. But the clouds don't clear. All the preparation has come to nothing. Time on these huge telescopes is precious, and theirs has run out. This ambitious test of quantum entanglement must wait. Anton Zeilinger was first captivated by the concept of entanglement as a young researcher in the 1980s.
I did not go to a single hour at the University of Quantum Mechanics. I learned it all from books. And when I read the books, it was clear that people evaded the question, what does it mean? They pretended everything is clear, but it was not so clear. The mathematics is fantastic. It's so beautiful that one can only regret that not everybody can appreciate it. But what the heck is behind it?
Anton began to experiment with entanglement in the lab. As new technologies developed, he was able to perform remarkable quantum trickery.
What happens if instead of 2 particles you have 3? Nobody knew. And it was my goal from then on to realize that in the lab. And it took me 10 years until I had that. What at that time we could do was create pairs of entangled particles. So you have a pair and another pair. And then what you do is you kind of mix these 2 photons, and take one out of the system, and then you are left with 1, 2, 3. 1, 2, 3. And if you do it right, then this photon doesn't know whether it belongs to this partner or this partner. And that way they all three become entangled.
Today, cutting-edge labs around the world are racing to harness Anton's multi-particle entanglement to create revolutionary new technologies, like quantum computers.
In our everyday computers, the fundamental unit of computing is a bit, a binary digit, 0 or 1. And inside the computer, there's all these transistors which are turning on and off currents. On is 1, off is 0. And these combinations lead to universal computing. With a quantum computer, you start with a fundamental unit that's not a bit, but a quantum bit, which is not really a 0 or a 1, but it can be fluid.
A quantum bit makes use of the fuzziness of the quantum world. A qubit, as it's known, can be a 0 or 1 or a combination of both. A particle or tiny quantum system can be made into a qubit, and groups of qubits can be linked with entanglement to create a quantum computer. The more qubits, the greater the processing power. At Google's quantum computing laboratory in Santa Barbara, the team has recently created a single chip that holds 72 qubits, more than any other quantum chip produced to date. The task for researcher Marissa Agostina and her colleagues is to send signals to these microscopic qubits to control and entangle them.
Mounted on the underside of this plate, we have the quantum processing chip itself. In essence, a quantum playground, you could say. Each qubit is a quantum object that we should be able to control at will. Thinking about it as the faster version of that PC over there would be a great slight to this. It can be much more than that. For instance, if we want to understand how some chemical reaction works, rather than using a mathematical model, we can use these qubits to model the chemistry.
By using entangled qubits, quantum computers could tackle real-world problems that traditional computers simply can't cope with. For example, a salesman has to travel to several cities and wants to find the shortest route. Sounds easy. But with just 30 cities, there are so many possible routes, it would take an ordinary computer, even a powerful one, hundreds of years to try each one and find the shortest. But with a handful of entangled qubits, a quantum computer could resolve the optimal path in a fraction of the number of steps. There's another reason teams like Marissa's are racing to create a powerful quantum computer: cracking secret codes. In today's world, everything from online shopping to covert military communications is protected from hackers using secure digital codes, a process called encryption. But what if hackers could make use of quantum computers?
A quantum computer could crack our best encryption protocols in minutes, whereas a regular computer or even a supercomputing network today couldn't do it, given months of time.
But while quantum entanglement may be a threat to traditional encryption, it also offers an even more secure alternative. A communication system that the very laws of physics protect from secret hacking. Researchers in China are leading the way. Here in Shanghai, at the University of Science and Technology, Professor Jian Wei Pan runs a leading quantum research center. His teams are working to harness the properties of the quantum world. They can send secret messages using a stream of photons in a system that instantly detects any attempt to steal the information. including digital phone calls that in theory are impossible to hack into.
So what have we got in here?
So here is a system for the secure telephone. Yeah? This is a fiber connection between two systems to send secure information. Hello， 哎，这飞虎啊，你这个头可以往下那个一点，对吧？哎，飞虎啊。
哎，庞老师。
你好啊。You can try.
Yeah.
You can hear.
Yeah.
It's very clear.
Jianwei's team has created a network of optical fibers more than 1,000 miles long that can carry secure information from Beijing to Shanghai. It's used by banks and data companies.
Here is all the cities which are connected to the network. For example, here is Shanghai. Here is China Bank. And here is our control center. So people are really using the secure information transfer.
But there is a limit to how far quantum signals can be sent through optical fibers. To send signals further, Jianwei's team launched the world's first quantum communications satellite. Above Earth's atmosphere, there are fewer obstacles, and quantum particles can travel much further. Each night, teams on the ground prepare to track the satellite across the sky. Laser guidance equipment locks onto the satellite to allow signals to be sent and received. The team aims to use this equipment to create a new secure communication system using quantum entanglement. The satellite will send entangled photons to two users. An eavesdropper could intercept one of the entangled photons, measure it, and send on a replacement photon. But it wouldn't be an entangled photon. Its properties wouldn't match, and it would be clear an eavesdropper was on the line. In theory, this technique could be used to create a totally secure global communication network.
So the next step is we will have ground station, for example, in Canada and also in Africa and many countries. So we will use our satellite for the global quantum communication. We want to push this technology as far as possible.
These are the first steps of a completely unhackable quantum internet of the future, made possible by quantum entanglement. But there's a problem. What if the loophole in our experimental proof of entanglement exists, and spooky action at a distance isn't real after all? It could mean entangled photons are not the path to complete security. So by using light released from quasars, the team in the Canary Islands is hoping to close this loophole and prove that entanglement is as spooky as Bohr always claimed.
This is not my experience.
Dominic and Jason are at one telescope.
Hello, Anton.
Anton is at the other.
Wir hatten gerade schon den Quasar im Field of View oder in der Iris.
Mit der Quelle funktioniert auch.
Ja, Quelle funktioniert, der Kontrast ist super. Läuft.
Das liegt jetzt.
Okay. Ciao.
With clear skies finally overhead, the huge telescopes awaken. Poised to collect light from distant galaxies.
Moving.
Dominic, is this the Darkon level or is the speed forever?
Arrive.
Darkon level.
Okay, this is good.
So we're doing everything at once now. So the guys for the links are setting the state of the entangled photon pair. We try to acquire the quasar. We're just centering it and making the field of view as small as possible to be sure that we only have the quasar.
Okay.
It's guiding now?
Yes, let's wait one more image.
Okay.
Of this one.
All right.
Great.
Yes.
Okay.
Ja, hab's gehört.
looks like 90, let's say 91 to be conservative, of purity.
With the telescopes now locked onto two different quasars, the team begins to take readings from their equipment.
Red counts 12,000, blue counts 7,000.
We do the full cosmic bell test.
What?
Yeah, we're doing a full cosmic bell test.
It's working. Light from the quasars is selecting which filters are used to measure the entangled photons.
It is exciting. It is. Now we do have a test, but it's not clear what the outcome will be.
Everything's exactly the same, beautiful, perfect. Yeah.
2 months later, back in Vienna, the team analyzes the experimental data.
This might take a second. The numbers look really great, and it is extremely pleasing to see that all this works so nice. We clearly see correlations that correspond to quantum mechanics.
The results show entanglement. The data shows that the pairs of photons correlated more than Einstein's physics predicts. And since the light from the quasars controlling the test was nearly 8 billion years old, it's extremely unlikely that anything could have affected its random nature. This remaining loophole seems to be closed. It seems Einstein was wrong.
The experiment we did is just fantastic. The big cosmos comes down to control a small quantum experiment. That in itself is beautiful. I think to do these experiments is a question of honesty. You have to do them. As long as there are loopholes, you have to close them as much as possible. This I consider an obligation.
You know, honestly, I still get chills. I mean, when I realized what our team was able to do in this intellectual journey that stretches back to the early years of the 20th century, there's hardly any room left for a kind of alternative Einstein-like explanation. We haven't ruled it out, but we've shoved it into such a tiny corner of the cosmos as to make it even more implausible for anything other than entanglement to explain our results.
Accepting that entanglement is part of the natural world around us has profound implications. It means we must accept that an action in one place can have an instant effect anywhere in the universe, as if there's no space between them. Or that particles only take on physical properties when we observe them. Or we must accept both.
We're left with conclusions about the universe that make no sense whatsoever. Science is stepping outside of all of our boundaries of common sense, and yet finding ways to explain the universe. It's almost like being in Alice in Wonderland, right, where everything is possible.
It was first seen as an unwelcome but unavoidable consequence of quantum mechanics. Now, after a century of disputes and discoveries, spooky action at a distance is finally at the heart of modern physics. At the Institute for Advanced Study, where the concept of entanglement was first discovered, researchers are using it in powerful new ideas that could lead to a single, unified theory of the universe, the holy grail of physics. Einstein's theories of special and general relativity perfectly describe space, time, and gravity at the largest scales of the universe. While quantum mechanics perfectly describes the tiniest scales, yet these two theories have never been brought together.
So far, we've not yet had a single complete theory that is both quantum mechanical and reproduces the prediction of Einstein's wonderful theory of general relativity. Maybe the secret is entanglement.
What we are learning these days is that in some sense quantum theory is really the dominant force, and that we might have to give up that what Einstein holds sacred, namely space and time. So he was always thinking, well, we have little pieces of space and time, and out of this we build the whole universe.
In a radical theory, known as the holographic universe, space and time are created by entangled quantum particles on a sphere that is infinitely far away.
What's happening in space, in some sense, all described in terms of a screen outside here. The ultimate description of reality resides on this screen. Think of it as kind of quantum bits living on that screen. And this, like a movie projector, creates an illusion of the three-dimensional reality that I'm now experiencing.
This wild idea may sound far-fetched, but it reveals that mathematically, the space and time we experience every day could be created by the quantum world. Entanglement could be what forms the true fabric of the universe.
The most puzzling element of entanglement, that somehow 2 points in space can communicate, becomes less of a problem because space itself has disappeared. In the end, we just have this quantum mechanical world. There is no space anymore. And so in some sense, the paradoxes of entanglement, the EPR paradox, disappears into thin air.
Truly understanding quantum mechanics will only happen when we put ourselves on the entanglement side, when we stop privileging the world that we see and start thinking about the world as it actually is.
Science has made enormous progress for centuries by sort of breaking complicated systems down into parts. When we come to phenomena like quantum entanglement, that scheme breaks. When it comes to the bedrock of quantum mechanics, the whole is more than the sum of its parts.
The basic motivation is just to learn how nature works. What's really going on? Einstein said it very nicely. He's not interested in this detailed question or that detailed question. He just wanted to know what were God's thoughts when he created the world.